Hi there, in this video I want to talk about section 1.1 from our textbook, and we're going to start with the properties of real numbers. So first let's talk about some of the real numbers, and these are some properties of the negative numbers. And so when you multiply a negative by a regular number, regular real number, you just get the opposite of that. And so here are some examples you can kind of go through. This is a review of your intermediate algebra. So negative times a negative gives you a positive. When you multiply a negative and a positive, you get negative. So some of the rules, when you multiply a negative by another negative, again, you get a positive. And here are some examples, and then the distributive property as well. So let's talk about what are some sets of real numbers. So we're going to go over the different sets that you may know. And I'm going to apologize as I get reacquainted with my writing tablet. My handwriting will get better as the semester progresses. So we have the smallest set is what's called the natural numbers. In the natural numbers, there's the set that starts with 1. And sometimes it's also called the counting numbers. It's 1, 2, 3, 4, 5, 6, and it goes all the way to infinity. Then when you add in for the whole numbers, we're going to add in just one thing, and you might already know what that is, 0. So we throw in 0, and you have the whole numbers. After we have the whole numbers, a slightly bigger set is the integers. Oops. And you probably have worked a lot with the integers already. So the integers are the whole numbers, and you throw in the negative counting numbers. So this goes all the way to negative infinity, and you have all essentially, sometimes it's called the negative whole numbers as well, and goes on to infinity in that pattern. But that's not the biggest set. So natural numbers are the smallest, then you go whole numbers, you add in 0, then you go integers, you throw in the negative counting numbers, and then what's the next larger set? Well, throw in all the fractions. So this set is just you building from small to largest. So when you add in the fractions, you get the set that's called the rational numbers. And this is not as easy to list because there are so many fractions, so we can't even, just between 0 and 1, you have an infinite number of fractions, right? You have 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, 1/10, 1/11. You get the point. So we have infinitely many fractions in there, so there's no way we could list them. So the rational numbers, sometimes you'll just see that it says something like a number is a set that consists of numbers of the form R over M, where R and M are integers, and M is not 0 because you cannot divide by 0. So examples of rational numbers: anything that can be written as a fraction, right? So 2/3 is a rational number, 1/2. 7 is a rational number. Why is 7 a rational number? It can be written as a fraction, right? This is 7 over 1. What else? 1.2 is a rational number because it can be written as a fraction. 0.33 repeated, that's also, it comes from 1/3. So these are the examples of rational numbers. So a rational number, think of anything that can be written as a fraction is a rational number. So when you think of decimals, it will be a terminating decimal or a repeating decimal. Those can be written as a fraction. And then the irrational numbers, this definition is probably the funniest one because it's just not rational. So all numbers that are not rational. So can you think of examples of rational numbers. Sorry, of irrational numbers. So the most famous one is pi. So you have pi, you have e, what else? Anything that is the square root that you can't take the square root of. So square root of 2, square root of 3, pi over 2, things that anything that already involves an irrational number then is considered irrational as well. So the square root of 21, things like that. So back to rationals up here, I could say the square root of 16, right? The square root of 16 is equal to 4, and so that will be a rational number. Whereas over here, the square root of 21, I cannot simplify it, so it is not rational. So it's considered irrational. Same thing with other radicals. So I could do the cube root of 2, right? I can't do the cube root of 2, so that will be considered irrational, and they cannot be written as a fraction. So those are our examples of irrational numbers. So some things you might see is if I give you the set, right, given the set, let me write it over here, negative 1.4, 0.22 repeated, square root of 3, pi, 4, 7 halves, 11 thirds, let's say the square root of 27, and let's say that's it. So can you from here identify the numbers that are natural numbers? So what values from this set are considered natural numbers? And remember, natural numbers is essentially just positive counting numbers. So the only natural number here is 4. What about whole numbers? Whole numbers is essentially the natural numbers with 0, and 0 is not in here. So the natural numbers in this will also just be 4. Sorry, the whole numbers here. And what about integers? So integers includes the positive whole numbers and the negative whole numbers. And of the negatives, I see a negative 1.4, but that's not a whole number, right? So then this will be also 4 is the only integer. What about rational numbers? So rational numbers, we have actually quite a few. There's negative 1.4, right? This is a terminating decimal. You have 0.22. This is a repeating decimal. So that's rational 4. Then 7 halves. It can be written as a fraction. 11 thirds. And that's it. And so what about the irrational? So the irrational number here will be the square root of 3, pi, and the square root of 27. Now together, the rational and the irrational numbers, they make the set that's called the real numbers. So when you see something say the real numbers, that includes everything, the rational and the irrational. So that is our largest set when we work in algebra. And so some of the properties with real numbers, so let me just write, the real numbers are the rational and irrational numbers combined. So that makes up your real numbers. And so the properties, so going up above when we did the properties of those negatives, this is assuming that a is a real number. So it can be rational or irrational. And again, remember, the rational numbers include the integers. The integers include the whole numbers include the natural numbers. So it's kind of like a nested sets. So the rational numbers are the biggest ones. And then the irrational numbers, those don't overlap, but together they make the real numbers. So some properties of real numbers include, and you might remember this from your intermediate algebra class. So we have the commutative properties, and we have it for addition and for multiplication. So I'm going to separate them. So the commutative property is if I have A plus B, that's the same thing as saying B plus A. So the order in which you add them doesn't affect the outcome. For multiplication is A times B is the same as B times A. So that's why when we say 3 times 4 is the same thing as 4 times 3, which is 12. So that's the commutative property. Then we also have the associative property, which is when you have three numbers. If I have A plus B plus C, that's the same thing as saying A plus B plus C. So as long as it's addition, you can add out of order, essentially. And same for multiplication. If I have A times B times C, that's the same thing as saying A times B times C. And so sometimes an example of when this might be useful, if you have something like, let me say 5 times 11 times 2, for example. So then you're like, okay, it's easier to do 5 times 2, so you can say this is the same as 5 times 2 times 11, because then 5 times 2 is 10, and then times 11. It's easier to do. So that's, as long as it's multiplication, you can multiply out of order. And then we have our distributive properties. And so distributive, it combines multiplication and addition or subtraction. So distributive is if I have A times, say, B plus C, then I have AB plus AC. And for subtraction, if I have A times, say, X minus Y, then you have AX minus AY. So these are our properties of the real numbers. Okay, so now let's talk about some set operations with real numbers. So the operations that we can have are union of sets, and we can also have the intersection of sets. So let's try an example. If I have two sets, say I have the set A is the even numbers 2, 4, 6, 8, and 10, and set B is something a little different, say 2, 3, 6, 7, 10, and 11. So when I say A intersect B, the intersection of two sets are the things that they have in common. So the values in common. So what do A and B have in common? So here A intersection B will be a new set, and let's see, the things that they have in common are 2, 6, and 10. So this will only have 2, 6, and 10. So the intersection is what do they have in common? And then the union, so if I'm asking you to find A union B, the union is as it sounds, you just put the two sets together. So A union B would be everything that's in A combined with everything that's in B. Now notice that because 2, 6, and 10 are already in A, I don't need to list them twice. So essentially it will be 2, 3, 4, 6, 7, 8, 10, and 11. So the things that they already have in common, we only list them once. So that would be A union B. So intersection is what do they have in common, and the union is just throw everything together. Some of the sets, real numbers, can also be written in set builder notation and in interval notation. So let's talk about what that is. So set builder notation in interval notation. So let's try an example. Set Builder notation is the notation with the braces, the curly bracket. So this says x such that, say, x is less than or equal to 5. So you can describe this set. So this is set builder notation. You can describe it in a number line by saying, well, I'm going to graph that. So I'm going to go to 5, and it says x less than or equal to 5. So equals, that means I fill it in, and then you shade everything that is less than 5. So then you can write this in interval notation, which will be, since it goes on forever, there's no end, it just says x is less than or equal to 5, and we are in the real numbers, we assume we go to infinity and negative infinity. So this will be negative infinity all the way to 5. Because 5 is included, it has the equals, we use a bracket. Let's try a different example. Say I have a different set. Expressed in set builder notation will be all x's in the real numbers such that negative 2 is less than or equal to x less than or equal to, actually let me just say less than 3. So you can directly write this to interval notation. Some of you may want the number line still as an intermediate step. So I will put -2 and 3. So it says x is between -2 and 3, but it is allowed to be -2 because it has the equal. So I'm going to put a circle on -2, fill it in. I'm going to shade everything between -2 and 3, but when I get to 3, 3 is not allowed to be a value for x, so that's an open circle. So in the interval notation, this will mean, do I have a bracket or a parenthesis at -2? Well, -2 is included, so it will be a bracket, and 3 is not included, so 3 will have a parenthesis. And so this is our set builder notation, interval notation, and so from here I could ask you all kinds of things like, what is the distance? What is the length of that interval? Right? So the length of the interval is essentially the distance between -2 and 3. So what is the distance between -2 and 3? So the distance between -2 and 3 is the difference in them. But remember, distance is positive, so we're going to say the absolute value of 3 minus a -2. So the length of the interval is 5. And you can see it here that that is true because you're going to have 0 somewhere in here. So to the left of 0 you're going to go 2, and to the right of 0 you're going to go 3. So 2 plus 3 is 5. So the distance is 5. So the absolute value is really what does the distance. So if I want to say the distance between A and B, A and B will be denoted as D equals the absolute value of B minus A. Absolute value is really what's giving you the distance between two numbers. So when you see things like the absolute value of 5 is 5, right? And or the absolute value of -7 is 7, you're really here saying the distance between, so this one is saying the distance between 0 and 5. Right, so that what that would look like is the distance between 0 and 5, which is the absolute value of 5, which is 5. The distance between, for the absolute value of -7, the distance between 0 and -7 would be D equals to -7 minus 0, which is the absolute value of -7, which is 7. So the absolute value is really giving you the distance of something.